Welcome to a journey beyond the stars, where science and imagination collide to unveil the deepest mysteries of the universe. For centuries, humanity has gazed at the night sky, filled with wonder and curiosity, pondering the vast expanse above and the origins of the cosmos. From ancient civilizations mapping the constellations to the revolutionary discoveries of Copernicus and Galileo, our quest to understand the universe has been an enduring and ever-evolving pursuit. But today, we stand at the dawn of a new era. With the James Webb Space Telescope, JWST, we are no longer just passive observers of the cosmos. We are explorers, traveling through time and space, unlocking secrets that have remained hidden for billions of years. This is not just another telescope, it is the most advanced space observatory ever built, capable of reshaping our understanding of the universe in ways we could only dream of before. For decades, the Hubble Space Telescope has been our primary window into the universe, capturing breathtaking images and providing invaluable scientific data. However, Hubble primarily observes invisible and ultraviolet light, limiting our ability to peer through thick cosmic dust clouds or detect the faintest, most distant galaxies. This is where JWST revolutionizes space exploration. Designed to operate in the infrared spectrum, it has the unparalleled ability to penetrate cosmic veils and reveal celestial objects formed just a few hundred million years after the Big Bang. Each image it captures is akin to a time machine, allowing us to witness the birth and evolution of the universe itself. But the road to building JWST was far from easy. Why did it take over 25 years and nearly $10 billion to create? Why is it considered one of the greatest astronomical achievements of all time? Unlike Hubble, which orbits close to Earth and has been serviced multiple times by astronauts, JWST was designed for a one-way mission. Stationed 1.5 million kilometers away at the Lagrange point 2, L2, a location where Earth's gravitational forces provide a stable environment for deep space observation. Its construction required overcoming immense engineering and scientific challenges, from developing an ultra-lightweight 6.5-meter primary mirror made of 18 hexagonal gold-coated segments, to designing an intricate 5-layer sunshield the size of a tennis court, each layer thinner than human hair, to protect its instruments from the sun's heat. More than just an instrument, JWST is a testament to human ingenuity and perseverance. It is the culmination of decades of work from thousands of scientists, engineers, and visionaries across multiple space agencies, including NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Its mission is clear: to explore the first galaxies, analyze the atmospheres of distant exoplanets, and search for clues about the origins of life itself. In this documentary, we will delve into the extraordinary story of JWST, its conception, the hurdles it overcame, and the groundbreaking discoveries it is making. Join us as we embark on a journey to unravel the cosmos with the most powerful telescope ever built. The journey of the James Webb Space Telescope, JWST, began in 1996, when NASA, in collaboration with the European Space Agency, ESA, and the Canadian Space Agency, CSA, envisioned a next-generation space telescope. At the time, the Hubble Space Telescope, HST, had already provided groundbreaking discoveries, capturing stunning images of deep space and revolutionizing our understanding of the cosmos. However, Hubble had its limitations, particularly in observing the infrared spectrum, a critical wavelength for detecting faint, distant galaxies. To push the boundaries of space exploration, astronomers and engineers proposed the Next Generation Space Telescope, NGST, an ambitious project designed to surpass Hubble. The initial plan was for a telescope with an 8-meter mirror and a budget of approximately $500 million, aiming for a launch in the early 2000s. However, as researchers refined its design, it became clear that such a telescope would require unprecedented advancements in technology and a much larger investment. In 2002, the project was officially renamed the James Webb Space Telescope, honoring James E. Webb, the NASA administrator who played a pivotal role in the Apollo program. Under his leadership, NASA expanded beyond space travel, investing in space science that would lead to groundbreaking discoveries in astronomy and planetary exploration. Naming the telescope after Webb was a tribute to his contributions in advancing space research. Overcoming engineering challenges. Building JWST was not just about making a bigger and better telescope. It was about rewriting the rules of space telescope design. Unlike Hubble, which orbits just 547 kilometers above Earth and could be serviced by astronauts, JWST would be stationed 1.5 million kilometers away at Lagrange Point 2, L2. This meant that once it was launched, there would be no chance of repairs or maintenance. Every component had to be built and tested to perfection before launch. One of the most innovative aspects of JWST was its primary mirror, designed to be 6.5 meters in diameter, more than 2.5 times larger than Hubble's mirror, 2.4 meters. This massive mirror had to be folded inside the Ariane 5 rocket, then unfolded and aligned precisely in space. To achieve this, scientists developed an unprecedented segmented mirror system consisting of 18 hexagonal segments, each gold-coated to optimize infrared light reflection. But why gold? Gold is highly reflective in the infrared spectrum, making it the perfect material to maximize JWST's sensitivity to deep space objects. However, pure gold would be too heavy, so engineers applied a microscopically thin layer of gold, 100 nanometers thick, onto beryllium mirror segments, a material known for its lightweight and extreme durability in space. Aligning these segments was another colossal challenge. Each mirror piece had to be adjusted with nanometer precision, meaning a deviation of even a fraction of a human hair could cause the telescope to malfunction. NASA developed a system of cryogenic actuators, allowing each mirror segment to be finely tuned in the vacuum of space, ensuring they worked as a single, perfectly focused unit. The sunshield, engineering a cosmic umbrella. Another monumental challenge was designing JWST's 5-layer sunshield, a structure larger than a tennis court, yet thinner than a human hair. Unlike Hubble, which operates at temperatures close to 0 degrees Celsius, JWST needed to be extremely cold, minus 223 degrees Celsius, or minus 370 degrees Fahrenheit, to detect faint infrared signals from distant galaxies. Even a slight increase in temperature could generate heat radiation, interfering with JWST's observations. To maintain this ultra-cold environment, scientists developed a sunshield made of Kapton, a high-performance polymer known for its ability to withstand extreme temperatures. Each of the 5 layers was strategically designed to progressively reduce heat, ensuring that the side facing the sun remained hot, while the telescope itself stayed frigid cold on the other side. However, deploying such a delicate structure in space presented another challenge. The The sunshield had to be folded tightly inside the rocket, and then autonomously unfolded once JWST reached space. This deployment involved over 100 mechanical release mechanisms, and if even one of them failed, the entire mission could be jeopardized. In 2018, a major setback occurred when a test of the sunshield resulted in a catastrophic tear, delaying the mission by several years. Engineers had to go back to the drawing board, reinforcing the materials and refining the deployment sequence. Every component was meticulously tested to ensure it could survive the extreme conditions of space travel, pushing the boundaries of cryogenic technology. Infrared observations require instruments to be kept extremely cold, far beyond what traditional cooling methods could achieve. One of JWST's most advanced instruments, the mid-infrared instrument, MIRI, required a temperature of -266 degrees Celsius, or -447 degrees Fahrenheit, just 7 degrees above absolute zero. To reach this temperature, NASA developed a sophisticated cryogenic cooling system, which worked like an advanced space refrigerator. Unlike traditional cooling methods, JWST's cryocooler had to function without generating vibrations, which could interfere with the telescope's delicate alignment. This system took over a decade to perfect, as even the smallest mechanical error could compromise the mission. Budget overruns, political setbacks, and near cancellation. Originally scheduled for launch in 2007, JWST faced multiple delays due to design refinements, funding issues, and technical failures. Its budget ballooned from $500 million to nearly $10 billion, drawing criticism from politicians and the public. In 2011, the U.S. Congress nearly canceled the project altogether, arguing that it had become too expensive and unmanageable. However, the astronomical community fought back, highlighting JWST's potential to revolutionize space science. After intense lobbying from scientists, engineers, and space enthusiasts, funding was reinstated, but with strict oversight to prevent further overruns. Despite these obstacles, the dedication of thousands of engineers and scientists across the globe kept the mission alive. JWST was no longer just a NASA project. It had become a symbol of human perseverance, scientific ambition, and the relentless pursuit of knowledge. Preparing for launch. The final steps. By 2020, JWST was finally complete, but launching such a complex machine was still a high-risk endeavor. The telescope had over 300 single points of failure, meaning if just one component malfunctioned, the entire mission could be lost. NASA subjected JWST to a series of rigorous tests, including thermal vacuum testing to simulate the extreme temperatures of space, vibration tests to ensure it could withstand the intense forces of launch, optical alignment checks to guarantee that its segmented mirrors functioned as a single unit. Finally, in 2021, JWST was carefully transported to the Guyana Space Center in French Guiana, where it would be launched aboard an Ariane 5 rocket, one of the most reliable launch vehicles in history. On December 25, 2021, the world watched as JWST lifted off into space, marking the beginning of a new era in astronomy. After over 2 decades of challenges, setbacks, and triumphs, JWST was finally on its way to unlocking the secrets of the cosmos. A testament to human ingenuity. The James Webb Space Telescope is more than just a scientific instrument. It is a monument to human ingenuity. Its journey from concept to launch is a story of relentless perseverance, engineering brilliance, and a shared vision to push the boundaries of knowledge. As JWST embarks on its mission, it promises to reveal the deepest mysteries of the universe, forever transforming our understanding of space and time. And this is just the beginning. The launch and deployment. A high-stakes mission. A one-way journey. The challenge of placing JWST in space. Unlike the Hubble Space Telescope, which orbits Earth at 547 kilometers, the James Webb Space Telescope, JWST, was designed for a one-way journey to deep space, stationed 1.5 million kilometers away at Lagrange Point 2, L2. This decision was made to ensure JWST's instruments remained ultra-cold, shielded from the heat of the Sun, Earth, and the Moon. However, this also meant that, unlike Hubble, which has been serviced multiple times by astronauts, JWST would never be repairable once launched. This single fact made every step of JWST's launch and deployment a high-risk operation. If anything went wrong, there would be no second chances, no fixes, and no possibility of recovery. Every component had to work flawlessly, and the deployment process had to be executed with zero margin for error. Given the stakes, NASA and its partners, the European Space Agency, ESA, and the Canadian Space Agency, CSA, spent years meticulously planning and testing every aspect of the launch and unfolding sequence. The final preparations for launch JWST was assembled and rigorously tested at NASA's Goddard Space Flight Center before being transported to Northrop Grumman's facility in California, where it underwent its final integration and testing. The telescope then embarked on a 16-day ocean voyage aboard the MN Colibri, a specially designed transport vessel, to the Guiana Space Center in French Guiana, South America, ESA's premier launch facility. Transporting JWST was an immense challenge in itself. The telescope had to be carefully packed into a climate-controlled shipping container to protect it from moisture, dust, and vibration. Even the smallest contamination could have jeopardized the mission. Every step of the transport operation was monitored with extreme precision. NASA selected Ariane 5, one of the most reliable launch vehicles in history, to carry JWST into space. Operated by the European Space Agency, ESA, Ariane 5 had a long track record of successful missions, particularly for deploying high-value satellites and interplanetary probes. However, launching JWST required some modifications to Ariane 5's usual flight plan. Engineers made structural adjustments to ensure the rocket's payload fairing, the protective shell covering the telescope, could accommodate JWST's massive folded structure. Additionally, special shock-absorbing systems were installed to minimize vibrations during liftoff, preventing damage to JWST's delicate optics and instruments. December 25, 2021. A Christmas Day launch like no other. On the morning of December 25, 2021, after years of anticipation, JWST was finally ready for launch. The world held its breath as Ariane 5 roared to life, lifting off from launch pad ELA-3 at the Guiana Space Center. Within just 27 minutes, JWST had successfully separated from the rocket and was on its way to Lagrange Point 2. The launch itself was flawless, but the real challenge was just beginning. Unlike most missions where deployment happens within hours or days, JWST's unfolding process would take an entire month. a highly intricate, high-risk sequence. Every step had to go exactly as planned, with over 300 single points of failure, meaning if just one critical mechanism failed, the entire mission could be lost. The month-long deployment, engineering's most complex ballet. Unlike the Hubble Space Telescope, which was deployed almost immediately after reaching orbit, JWST's unfolding sequence was the most complex spacecraft deployment ever attempted. The deployment consisted of 5 major phases, each requiring extreme precision. Within 30 minutes of separating from the rocket, JWST deployed its solar array, ensuring it could generate power. This was the first critical step. Without power, none of the other deployments would be possible. The solar array unfolded flawlessly, marking the first major success of the mission. Next, JWST extended its high-gain antenna, which was crucial for establishing continuous communication with Earth. This allowed NASA's Deep Space Network, DSN, to receive real-time updates on JWST's status and progress. Unlike other telescopes, JWST had no direct connection to Earth. It had to use this antenna to send scientific data back. One of the most nerve-wracking parts of JWST's deployment was the unfolding of its 5-layer sunshield. This sunshield, which had been folded tightly inside the rocket, had to be deployed in space with absolute precision. Over a period of 8 painstaking days, engineers on Earth remotely controlled the unfolding sequence. The sunshield was slowly tensioned into its final form, layer by layer, with each layer reducing the heat transfer from the Sun by more than 100 times. This was the most complex and failure-prone part of the deployment. If the sunshield failed, JWST would overheat and be rendered useless. NASA described this moment as watching a miracle unfold in real time, as each layer successfully locked into place. With the sunshield successfully deployed, JWST could now focus on its optics. The secondary mirror, a crucial component for focusing incoming light onto JWST's instruments, was extended on a long boom arm. This mirror had to be perfectly aligned with the primary mirror to function correctly. Additionally, radiators were deployed to help cool JWST's instruments, preventing excess heat from interfering with observations. Finally, JWST's iconic 6.5-meter primary mirror, composed of 18 gold-coated hexagonal segments, was slowly unfolded and locked into place. Each mirror segment had to be adjusted down to nanometer precision to ensure they acted as a single, cohesive surface. Engineers used a sophisticated wavefront sensing system to calibrate the mirrors, a process that took several more months to complete. By January 24, 2022, JWST had reached Lagrange Point 2, successfully completing its journey. A triumph in space engineering. The successful launch and deployment of JWST was one of the most remarkable achievements in space exploration. Every single mechanism had worked flawlessly, defying the odds and paving the way for a new era of astronomical discovery. NASA scientists described the deployment as the most complex robotic ballet ever performed in space. JWST was now positioned to begin its science mission, opening a new window into the cosmos. As the world watched in awe, the telescope began calibrating its instruments, preparing to capture the first breathtaking images of deep space. Humanity had just sent its most powerful eye into the universe, forever changing the way we see our cosmic origins. Groundbreaking discoveries, unveiling the secrets of the cosmos. A new era of space. Exploration begins with its successful deployment and calibration. The James Webb Space Telescope, JWST, officially began operations in July 2022, marking the start of a new golden age of astronomy. Scientists had spent over 2 decades building and perfecting this telescope. And now, it was finally time for JWST to fulfill its mission. To peer deep into the universe, unravel its secrets, and challenge what we thought we knew about space. The first images sent back by JWST were not just scientific marvels, but awe-inspiring works of art, revealing the cosmos in unparalleled detail. These images provided insight into the earliest galaxies formed after the Big Bang, the life cycle of stars, from their birth in stellar nurseries to their explosive deaths, the atmospheres of exoplanets, revealing clues about potential life beyond Earth, the structure of the universe, including massive cosmic webs and dark matter interactions. But what exactly has JWST discovered? Let's take a deep dive into its most groundbreaking findings so far. Peering into the past, JWST's Deep Field Images. On July 12, 2022, NASA released JWST's first deep field image, showing SMACS 0723, a massive galaxy cluster located 4.6 billion light-years away. Why was this image so significant? Unlike previous telescopes, JWST could see much deeper into space, capturing thousands of galaxies in a single frame. But more importantly, it was the sharpest infrared image of the distant universe ever taken. Gravitational lensing, a natural magnifying glass. One of the most fascinating aspects of this image was the presence of gravitational lensing. The massive gravity of SMACS 0723 bent the light from even more distant galaxies behind it, magnifying them like a giant cosmic telescope. Thanks to this effect, JWST detected galaxies that formed less than 600 million years after the Big Bang, a feat previously thought impossible. Scientists were stunned by what they saw. Some galaxies were much more massive than expected for such an early period in the universe. The structures of these young galaxies were more developed than models predicted. The presence of old stars in these early galaxies challenged our understanding of galaxy formation. JWST had just rewritten the history of the cosmos, forcing astronomers to reconsider their models of the early universe. Building on the success of the SMACS 0723 image, JWST later captured the Pandora's cluster, Abell 2744, another massive galaxy cluster acting as a gravitational lens. This deep field image revealed galaxies that formed within 350 million years of the Big Bang, the oldest galaxies ever observed. Unexpectedly complex structures, including spirals and clusters, in a period where scientists expected only simple, small galaxies. Evidence of early black holes growing much faster than anticipated, suggesting they may have played a bigger role in galaxy evolution than previously thought. These discoveries challenged the lambda cold dark matter model, the standard theory of cosmology, forcing scientists to rethink how galaxies evolved in the early universe. The birth of stars, revealing stellar nurseries. One of the most breathtaking images from JWST was its capture of the cosmic cliffs, a region inside the Carina Nebula, located 7,600 light-years away. Hubble had previously imaged this region, but JWST's infrared vision revealed stars being born inside thick clouds of dust, something never seen before. What did we learn? JWST showed thousands of young stars, some only a few million years old. Scientists discovered protoplanetary disks, indicating that planets were forming around these newborn stars. The telescope detected shock waves from massive young stars, sculpting their surroundings and triggering new waves of star formation. This was the first time we had directly observed the chaotic, dynamic process of star birth at such a detailed level. Witnessing the death of stars, the Southern Ring Nebula. JWST also provided the clearest image ever taken of the Southern Ring Nebula, the remnants of a dying star. The dying star at the center was surrounded by intricate shells of gas, revealing how material is recycled in the universe. JWST confirmed that this star was part of a binary system, with a companion star helping shape its final explosion. The telescope detected carbon-based molecules, showing how essential elements for life are spread across space after a star's death. These insights help us understand how planetary systems like our own form from the remnants of old stars. Exploring exoplanets. Are we alone? One of JWST's most exciting missions is studying exoplanets, planets orbiting stars outside our solar system. JWST made history when it detected water vapor in the atmosphere of the exoplanet WSP-96b, located 1,150 light-years away. This was the first direct detection of water on an exoplanet using infrared spectroscopy. What does this mean? While WSP-96b is too hot for life, the discovery proves that JWST can analyze exoplanet atmospheres with unprecedented detail. This technique will be used to search for biosignatures, chemical signs of alien life. Another breakthrough came when JWST detected sulfur dioxide SO2 in the atmosphere of WSP-39b. Why is this important? It was the first direct evidence of photochemistry, chemical reactions triggered by starlight, on an exoplanet. This means complex atmospheric processes are occurring on other planets, potentially affecting their habitability. JWST is now scanning rocky planets in the habitable zone, searching for molecules like oxygen, methane, and carbon dioxide, which could hint at extraterrestrial life. Surprising discoveries in our solar system. Even within our own solar system, JWST has made groundbreaking observations. JWST confirmed that the asteroid Chariklo, located beyond Saturn, has a ring system, something previously thought to exist only around large planets. This raised new questions about how small objects can maintain stable rings, whether rings are more common than we thought in the solar system. JWST detected plumes of water vapor erupting from Europa, a moon of Jupiter. This supports theories that Europa has a subsurface ocean, which could potentially harbor life. The future of JWST's discoveries. JWST has already transformed our understanding of the universe, but its journey is just beginning. Over the next decade, it will search for biosignatures on Earth-like exoplanets, probe the first moments of the universe with even deeper observations, investigate dark matter and dark energy, uncovering the forces shaping the cosmos. Final thoughts. A new window to the universe. JWST is not just a telescope. It is a time machine, a portal to the earliest moments of existence. Its discoveries are redefining our place in the universe, proving once again that humanity's curiosity knows no bounds. The greatest discoveries are yet to come. The future of JWST and its legacy. JWST is not just a telescope. It is the beginning of a new age of discovery. Since its launch, it has transformed astronomy, uncovering mysteries of the universe that were once thought to be beyond our reach. But what comes next? The telescope's mission is just getting started. Over the next decade or more, JWST will continue to push the boundaries of knowledge, addressing some of the most profound questions in science. How did the first galaxies form? What is the true nature of dark matter and dark energy? Are there habitable planets beyond Earth? Could life exist elsewhere in the universe? Each of these questions represents a frontier of human understanding, and JWST is poised to lead the charge. One of JWST's primary missions is to study the first galaxies that formed after the Big Bang. Using its unparalleled infrared sensitivity, JWST has already detected galaxies that existed within 300 million years of the universe's birth. But how far back can it see? Astronomers believe that the very first stars in the universe, known as population 3 stars, were composed only of hydrogen and helium, as heavier elements had not yet been formed. These stars were massive, often 100 times the mass of the Sun, short-lived, exploding as supernovae within a few million years, crucial in shaping the early universe, seeding space with the first heavy elements. JWST has the capability to detect the remnants of these ancient stars, offering direct evidence for how the first elements beyond hydrogen and helium were created. If JWST finds direct signatures of population 3 stars, it will rewrite the story of cosmic evolution. The universe is not randomly distributed. Instead, galaxies form a vast structure known as the cosmic web, a network of dark matter and gas that spans billions of light years. JWST's observations of distant galaxies help astronomers map this structure and understand how galaxies are connected by filaments of dark matter, how gravity shaped the first cosmic structures, the role of supermassive black holes in shaping early galaxies. By studying these large-scale structures, JWST will help answer a fundamental question. Why does the universe look the way it does today? One of the most exciting aspects of JWST's mission is its ability to study exoplanets, planets orbiting stars beyond our solar system. But it's not just looking for planets. It's searching for signs of habitability and even life. JWST has already detected water, carbon dioxide, methane, and sulfur dioxide in the atmospheres of exoplanets. But the next goal is even more ambitious. Can JWST find biosignatures? Biosignatures are chemical markers that indicate biological activity, such as oxygen, O2, and ozone, O3, produced by photosynthetic life. Methane, CH4, and carbon dioxide, CO2, possible indicators of microbial life. Nitrous oxide, N2O, a potential marker of biological processes. JWST is currently studying Earth-like exoplanets in the habitable zone, where liquid water might exist. If it detects a combination of oxygen and methane in an exoplanet's atmosphere, it could be the first strong evidence of extraterrestrial life. One of the most promising planetary systems for life is TRAPPIST-1, located 39 light-years away. This system has 7 rocky planets, 3 of which orbit in the star's habitable zone. JWST is already studying these planets, searching for atmospheric composition, surface conditions, potential water vapor or clouds. If TRAPPIST-1 has a planet with an Earth-like atmosphere, it would be one of the greatest discoveries in human history. Dark matter makes up about 27% of the universe, yet we cannot see it. It only interacts with gravity. JWST is helping to solve the mystery by mapping dark matter distributions using gravitational lensing, studying how galaxies rotate, which reveals unseen mass, looking for dark matter annihilation signals. JWST could help us finally identify what dark matter is made of, something that has eluded physicists for decades. Dark energy, the force accelerating the expansion of the universe, makes up about 68% of the cosmos. But we have no idea what it is. JWST is measuring the expansion rate of the universe with unprecedented accuracy, helping scientists test theories about the ultimate fate of the universe. Will it expand forever or collapse? Whether dark energy changes over time, possible new physics beyond Einstein's equations. These discoveries could revolutionize our understanding of physics. While JWST is the most powerful telescope ever built, it is just the beginning. NASA's next major telescope, planned for the 2030s, will be the Habitable Worlds Observatory, HWO. It will be designed specifically to search for life on exoplanets, use direct imaging to photograph Earth-like planets, be able to study biosignatures in real-time. JWST is paving the way for this next-generation observatory. Other proposed missions include LUVOIR, Large UV Optical IR Surveyor, a telescope even larger than JWST, capable of imaging Earth-like planets in detail. Origins Space Telescope, a mission designed to study how planets and galaxies form in even greater detail. JWST's legacy will live on in these future telescopes, continuing humanity's quest to explore the cosmos. JWST was designed to operate for at least 5 to 10 years, but it could last much longer. Factors affecting its lifespan include fuel supply. JWST uses fuel to stay in orbit at L2, but efficient trajectory corrections have extended its potential lifespan to 15 to 20 years. Instrument degradation. Space radiation and micrometeoroids could eventually affect its performance. Unlike Hubble, JWST was not designed for servicing. However, future robotic missions could be developed to refuel JWST, extending its life by decades, upgrade its instruments, allowing it to remain competitive with future telescopes. If successful, JWST could remain operational for generations. JWST is more than a telescope. It is a monument to human ambition. It has already changed how we see the universe, and its discoveries will inspire generations to come. As we look up at the stars, JWST reminds us that the greatest mysteries of the universe are still waiting to be discovered. The journey has only just begun. Thank you for watching. If you enjoyed the content, don't forget to like and subscribe to support me.